the invitation. I'd like to thank my fellows that are collaborators for this work, Jean Carvalho, Antônio Prata, and Rodolfo Vilhena de Moraes, from Brazil. I also thank the organizers of the workshop for the kind invitation for this talk, and also the institutions involved. The topic that I'm going to talk about, it can be summarized, is a summary of research that I've been developing that can be accessed in these references that I showed you in the screen. Okay, the research motivations of the topic to use dynamical averaging maps to find stable orbits around celestial bodies with irregular shape. The main motivations are all the ones that you can see in the screen, but both theoretical and practical, because we can use this both for celestial mechanic interest and also for astrodynamics applications, especially to study orbits around bodies with irregular shape, for example, moons and planets like Mercury, and also asteroids that can be approached as an ellipsoid. The choice of variables that we use in this work is the classical set of variables that we call the orbital elements, and in order to integrate the motion, we use the classical Lagrange planetary equations, as you can see in the shape as presented by Kovalevsky. And the important thing in these equations is that the potential, the disturbing potential R, is where we are going to include all the forces. So if you want to add another force in the system, you have to write the disturbing potential and sum up within this force, this potential called R. The first perturbation that we take into account when studying a small particle, a spacecraft around a celestial body, you should consider the third body perturbation, because, for example, if you are orbiting a Galilean moon like Callisto or Europa, as we have missions that are planning to visit these bodies, maybe in the future, in the case of Callisto, but for sure in the case of Europa, we need to consider the perturbation from Jupiter, for example. In this case, we have the potentials, as you can see in the screen, and we expand to the factor to the index K2, that is called the quadrupolar expansion. People that work with, especially with exoplanetary investigations, for example, the stability of exoplanetary systems, there are some investigations that if you expand up to more terms, you can use the extra terms to describe the switch from prograde to retrograde orbits. But this is more extreme cases where you have very massive and complex systems. In our case, it's much more simple, because we consider this very small body, that is the spacecraft or the particle, could be a ring particle, around the celestial body, that in our case are going to be Callisto, the Jupiter, the Galilean moon, and also Mercury. After expanding, we can write the potential of the third body will be dependent on these variables alpha and gamma, and that can be written in this shape. However, as you can see, many variables are involved, and if you try to integrate the Lagrange planetary equations, the full dynamics of the system, what happens is that especially if you have a third body that is very far away from you, the computational code will be very big. So it's going to take a long time to integrate the system. So what we are going to do is to apply the concept of averaging in order to remove the short period effects and have a long-term disturbing potential to describe the qualitative evolution of the system, because these small oscillations, usually they are not important if we are going to look to the overall stability. If you are going to need precise navigation, in this case you should not remove these terms, or you could use the system, find the approximate solutions, and apply some technique to recover the short period effects after that. This is the way that you can write to apply the average over the third body perturbation. In order to perform this average, that we are going to remove the short period effects of the motion of the spacecraft, and we are also removing the short period effects of the motion of the third body, the perturbing body. as the potential is written in terms of the true anomaly, we need to adapt the integration in terms of mean anomaly or eccentric anomaly. So the expressions that you see in the screen are the ones that you can use to switch the potential and perform the integration, the average, in terms of either mean anomaly or eccentric anomaly. Other forces that we can consider in the modeling of the system are the forces due to the regular shape of the central body. In our case here, for the case of Callisto, we consider J2, that is C20, and C22, the flattening and the ellipticity of the equator of the central body. For the case of Mercury, we are going to add also the effect due to J3, that is just one order of magnitude smaller than the other forces. So in this case, in this case of Mercury, as J3 is enough close in magnitude to the other terms, we add this term to see his impact in the evolution of a particle around Mercury. In this case, after the application of the average, the mean anomaly, in the case we are removing, we change the potential to mean anomaly, and after we integrate in terms of the mean anomaly, we remove the mean anomaly. That's why we can remove one equation here, because mean anomaly will have a constant evolution. In this case, you can see the top potential will be an average potential of the third body, the J2 and C22, as we think about applications to the case of Callisto, as you can see. Here are a few plots using these potentials. We made some tests and we find circulation and libration, and compare with other models, and it's fitting well in terms of qualitative effects. This is just a test, and you can find orbits that are librating, orbits that are circulating. And the interesting thing here that is regarding the title of the talk is that we use I call dynamical average maps because we are performing dynamical maps, pairs of orbital elements, keeping the order fixed, and analyzing how the change in the other two parameters that are free, that we made free in the integration, how they are going to impact the lifetime of the orbits. In the case, in the bar that you see in the right of each plot is regarding an evolution of up to 1,000 or more days. In this case, for example, if we map the evolution in terms of initial argument of the percenter or initial longitude of the ascending node, we can find some islands and some regions where the evolution of the particle around Callisto, even with a big perturbation from Jupiter, we can find, and also it's interesting, even in the case of polar orbit, that usually is very disturbed, especially because of the quasi-Lidov effect, where we have a switch between eccentricity and inclination, which creates a collision, usually in a very short time. It's interesting because using these maps, we can observe regions where we can maximize the lifetime of the orbit. And if we pick these regions, we can find, for example, these initial conditions. And if we are outside of these regions, the plot you see in the right that has a big solution in terms of a big long-term stability in 19 degrees in the middle, the yellow light in the middle. If we are picking a map outside of the region where we are, for example, choose argument of the pericenter 180 degrees, what happens is that we don't have this line. The center is totally purple, for example, meaning that it's the spacecraft or the particle would survive in a polar orbit just for a few hundred days and would collide very soon after that. But in the case of using this specific value of, for example, argument of the pericenter 180 degrees, we can find a more stable region, and we can create this gap of stability in the perturbation map. Here there is an example of simulating orbits with similar parameters, but changing the initial value for the argument of the pericenter that we find in those stability regions in the previous maps. In the upper part of the screen, you can see that for polar regions, we always surviving up to 500 days. And if you look, pick one orbit from this purple region. In the right, you can see the evolution of the centricity along the time for example, 6,000 days. And you see that after a few hundred of days, all the eccentricities will reach the critical eccentricity, that is the eccentricity that will make the altitude of the pericenter to reach the same value than the radius of the central body, meaning that we have an impact in that moment. But if we choose the stable value that we found in the previous map for the argument of the pericenter, 180 degrees, for example, we see that we create these gaps of stability, these islands of stability in the polar region. And for specific values, we can play, for example, creating these two islands that you can see in the lower level, lower plot in the left. We have these stability islands around 90 degrees of longitude of the city node, and also around 270 degrees. And if you pick one orbit, and if you plot orbits that are inside these regions, you can see in the right and lower level, the lower plot, that there's no orbit that is oscillating the eccentricity in reaching the critical eccentricity that will create, that will make the altitude of the pericenter reach the same altitude as the radius of the central body, meaning that there's no impact in this case. So, we have how to test how strong is this stability. What we did, for example, in the case of these models here in these initial conditions, we have the first plot that you can see up in the left is a true simulation using the parameters of the Jupiter and Callisto system. So we have Callisto as central body and Jupiter the third body, and we have the true eccentricity of Jupiter. What we make to test how strong is the stability of the initial conditions that we found is to increase the eccentricity of Jupiter, because on doing that, the relative dynamics will make Jupiter and Callisto to approach much more. In this case, with the strong gravity of Jupiter, it tends to create less lifetime, smaller lifetime for the spacecraft. So we start to create maps increasing in creating fictitious systems where Jupiter is even more elliptical in its orbit around Callisto. I just show here 3 cases, but as you can see, even for 0.3 eccentricity of Jupiter around Callisto, this stability region is pretty strong. Even for in a specific range of tens of kilometers of altitude over Callisto, as you can see from the variation of the semi-major axis in the x-axis. Is interesting because it can be proved that this is useful to find regions where it can extend the lifetime of spacecrafts or particles. And potentially, for the case of particles, you could find for debris or a ring in that region that could be potentially be around, or small moons around that moon in the case of Callisto. In the plots above, in the top, are plots regarding orbit lifetime and initial inclination. As you can see, if you choose a value for the arguments of the pericenter outside of those stability islands, the lifetime for polar orbits is a few hundreds of days. But if you choose to select orbits for different values of semi-major axis and that are in the left, and different values of eccentricity that are in the right side, we see that for all the cases, the orbits will, the orbit's lifetime, setting this value that we find in the stability region, that is argument of the pericenter 180 degrees, we can extend a lot the lifetime of these orbits. So it's pretty interesting result. I didn't put here, but there is a work from a group in Rome, from Condoleo, Cerci, I think Cerci, his name, I think. And they have a work, analytical work, where they study the same system, but using vectorial formulation in terms of, and they try to find an analytical solution to find stability around Callisto. In this case, the regions they predict are exactly the same that we find here using these dynamical maps. And also there's another study that recently mentioned that Callisto is one very unique case of moon that has enough gravity and is far enough from the planets to have another moon around it, a moon of moon, or a ring or particles around. So it's a unique body in the solar system. So it's very interesting because all these results are fitting as with these older, more recent studies. But in the case of Mercury, we have solar radiation pressure acting there. It's interesting because the first time that I have contact with this was during a talk from Bill Nile during the IAC 2016, where he was talking about his mentor, that is Carl Sagan, that everyone knows him, and talking about future, the use of solar sails and solar radiation pressure in acting, especially in these regions where we're closer to the sun. And it was my first contact with this. And think about a Mercury orbit, we need to consider this kind of thing. And this is the picture where you can see the scheme where you have the concept of solar sail. The radiation from the sun hits the reflective film, and you have a resulting thrust in a specific direction that the engineers can control depending on the purpose, if it's a maneuver or it's just navigation for a further region. So this is the concept. In order to model this, we use these models here. As you can see, I plot here this 30 body perturbation together with the solar radiation pressure. Why? Because they both come from the sun. So the solar radiation pressure, sometimes you could interpret it as a minimization effect of the gravity of the disturbing body, having the sun as the 30 body. And it's very important because playing with this perturbation, with the parameter, especially beta, that is dependent on the area and the mass of the solar sail, we can provide the engineers with parameters to build and select the physical structure and shape of the and also the mass of the spacecraft to know how better minimize fuel consumption, to maneuver better. So it's an interesting topic. So when you put the two perturbations together, we have this format here. So in order to analyze a particle or a spacecraft or solar sail around Mercury, we have this disturbing potential. We have G2, G3, C22, the 30 body with solar radiation pressure. For example, if you start playing, the plots in the left are without J3, and the plots in the right are with J3. J3 has this peculiar characteristic, as I've mentioned, is just one order of magnitude below J2 and C22, and is able to create this asymmetry in the stability map, creating this region where you have more or less stability for the case of specific values of argument of the pericenter and also other parameters that you could be playing with. For example, if we choose mapping the final eccentricity that is going to impact if there's a collision or not, in terms of different values of argument of the pericenter, we can use those maps and plot some evolutions of different orbits in those regions. And as you can see, we can find regions where we can have minimal final eccentricity and maximal orbital time. Final eccentricity in the left, and minimal eccentricity in the right. In the lower plots, you can see that I have an idea of, okay, let's see for different values of eccentricity, for different values of semi-major axis, how much the final eccentricity or the orbit lifetime is having, how much is the variation if we change the initial value of all these parameters. As you can see, the value of around 0.02 eccentricity for the spacecraft around Mercury, considering these perturbations, is the one that you can change, select different values of the major axis, meaning that we are increasing the effects of solar radiation pressure and also the third barrier perturbation, even changing the altitude. This value of eccentricity keeps usually the same final value of eccentricity, meaning that it's pretty strong against the increase or the decrease of the perturbation. So it was for me an indication that this value could be a good player to be a good stable candidate eccentricity to select as a good stable region to place a spacecraft. For example, is a good application and insight for Bepi-Colombo when it arrives in Mercury in a few years. So picking those values that we can find using verifying these maps and also these trends about the final eccentricity, we can pick and find, of course, frozen orbits that are pretty stable orbits. We have some orbits that are oscillating above, but some we can find orbits that are librating in terms of eccentricity and argument of the pericenter, and we can find families of these stable orbits around these initial conditions that we find using this mapping. So the idea of using the dynamical averaging mappings means the dynamical map is using average models. It's pretty useful in order to find more stable regions around these bodies, and you can whatever number of perturbations that you put in the system, you can find and play with these perturbations. Some take one out or plug it in the system, and you can play and see how is the role of each force also in the system, as you can see in the right here. And it's interesting because when you couple C22 in the case of the Mercury, you see the C22 has this smoothing effect, decreasing the perturbation. So C22 acts in the case of Mercury, and usually in other cases, in general, we had another study mapping, verifying the effect of C22 in different moons of solar system and other bodies. Usually, C22 always play this role as a useful, as a helper, a supporter of the engineers in the case, or the objects that want to be stable, in order to minimize the perturbations of the other forces in the system. You can also map individual forces, as I've mentioned. But for the case of the solar radiation pressure, if you are in lower altitudes, the effects are not significant because the gravity effects are much more stronger in this case. But if we start to increase the altitude, the effect of the solar radiation pressure increases a lot, significantly, and the environment becomes so unstable. Here you can see different plots for different parameters of the solar radiation pressure that impact in different shapes and areas and masses for the solar sail. If we, in this high altitude, for example, 6,000 kilometers of semi-major axis around Mercury, the environment is so unstable that it's very hard to find stable orbits in this region. But we could find few families of stable orbits, but just when you select almost circular orbits of the order of 10 to minus 3. So some significance in the eccentricity of the spacecraft already creates instability in terms of find a frozen orbit that could be placed there to keep the variations of argument of the pericenter, inclination, eccentricity almost negligible in terms of saving operational costs and maneuvering around Mercury, for example. But is still we can be guided to find these stable conditions using those dynamical maps. So despite the environment is still unstable, we might not find in general many cases frozen orbits. However, we can find regions with minimal or maximum perturbation. That maximum perturbations can also be useful if you want to maneuver a spacecraft. You can use the gravity and the perturbations in the system to save fuel consumption. And so it's not a problem also to find regions with more perturbations. So in conclusion, these investigations were an expansion of the work, the PhD thesis of Jean Carvalho in 2011. That we expanded his work, including the inclination of the third body in the system, and also now we have a model with eccentricity and inclination of the third body. We could the methodology and the strategy are useful to identify regions with minimum perturbation and maximal lifetime for spacecraft or a particle around Callisto and Mercury. We could find frozen orbits around Mercury, and this contribution, this kind of strategy can also be used in the process to find individual contributions of forces, so you can quantify qualitatively how much each perturbation is influencing the system. Future possibilities for the continuation of this work are extension of the seminars to the celestial bodies, applications of these in both celestial mechanics investigations to find stability of moons around planets, or potentially find regions that can potentially are stable enough to have a ring there. Could apply it also to investigate the stability around ellipsoidal asteroids. We could include other forces in the system, of course. Here we included this one that are the main disturbing forces for these two bodies, but in other cases, we can consider other forces in the system. For instance, in the case of theirs, we could potentially include C31, S31, C32, S32. There are other terms that we can consider. And we can also, from these, have some ideas about developing a Hamiltonian formulation to take advantage of this and maybe find some other methods to investigate the stability of the system. So that's it. Thank you for your attention.
Thank you very much for the